In this video, we're going to be talking about a normal probability plot for residuals for the simple linear regression model. So just as a reminder, the simple linear regression model is yi equals beta naught plus beta 1 x sub I plus epsilon sub I, where epsilon sub I is the model error, and this goes for I equals 1 to n. Right? And there is the assumption for this model, if you want to do inference, like constructing confidence intervals, prediction intervals, hypothesis tests, you need this assumption that these error terms, epsilon sub I, are normally distributed. So that's what we're going to talk about in this video. Right? And so the assumption is that it's normally distributed, IID, identically independently distributed. So that means your error terms are uncorrelated, right? And their mean is 0 and the variance is sigma squared. Okay, the homogeneous variance assumption that they have the same variance for all I, right? They're identically distributed. And in this video, we're going to focus in on this normality assumption. So the assumption that their mean is 0 and they have the same variance, you need to check those assumptions first, okay? Once you've checked those assumptions, then you can go and check the normality assumption. So once again, very important you understand that this video is focusing on checking only that normality assumption, checking that the expected value of your error terms equals 0 and that the variance of your error terms equals sigma squared, the homogeneous variance assumption. You need to do this first, okay? All right, so now that you understand, we're checking just that normality assumption. Recall, we do not observe, right, these error terms, right? Instead, what happens? We go and get y hat, a predicted value of the outcome, which is b naught plus b1 x sub I, right? Where b naught and b1 are unbiased estimators, as long as these first two assumptions right here are true. So that's why these assumptions must be tested first, okay? So we can estimate this error term using the residuals, e sub I equals the observed value of the outcome, y, minus the predicted value of the outcome, y hat. All right? And if we think that, these error terms or these residuals are basically telling us, they're kind of like an estimate of that model error, epsilon. So if epsilon is normally distributed, then these residuals, we hope, are also normally distributed. And very first thing that we could do is go ahead and draw a histogram. A histogram is a great starting point. Okay, so a histogram of those residuals. And if you draw a histogram, you're hoping to see, a normal distribution. Okay? Now, another choice, in addition to doing a histogram is a great place to start. Another plot that you can draw is the normal probability plot. So this is another way to graphically see if those residuals are normally distributed. Normal probability plot. Okay, and there are a lot of different ways you can do normal probability plots, right? Excel will automatically produce a normal probability plot for you if you're using the data analysis tool pack. Personally, I do not use that graph. It's a little strange, and I'll talk a little more about the graph that Excel produces in my next video where I'll do an example. But the normal probability plot that I use and that a lot of people use, it's based on a statistical theory in order statistics, okay, that states that Z, and then I'm using the subscript in in parentheses like this to indicate that I'm ordering. Okay, so this is in order statistics. So I'm ordering these z values. Z, that's D, normal, 0, 1. Okay, so for k equals 1 to n, right, where k is the kth ordered, z value, right? The expected value of the kth, let me scroll down, smallest value is, okay, this is the inverse normal distribution, right? It's just a notation. Stands for the inverse normal distribution. And the value it takes is k minus 0.375 divided by n plus 0.25. Okay. So what's happening here? What did I just do? Right? If I have a normal distribution, okay, and I want to sample from it. So this is a normal 0, 1 distribution. And I want to randomly sample from it. Okay? So say I go out and I randomly sample 10 observations from that normal distribution. Okay? Then what this is telling me is where I should expect those 10 observations to be. All right? So the smallest observation, I would expect it to be maybe here, right? Then 2, 3, 4, 5, right? I would expect to have more observations. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, this is a rough graph, but you have less observations in the tail and more observations towards the center. Okay, so this value here, I can calculate exactly what it is based off of this guy. So if I have 10 observations, that value would be the inverse norm value at, okay, k would be 1 for the first observation, minus 0.357 divided by, if there's 10 observations, 10 plus 0.25. Right? And I could plug this into a calculator and it'll tell me exactly what this z value is. Okay? So these are basically the expected z values. These are the expected z values of ordered z values. Okay? If you have this normal 0, 1 distribution. Okay? So epsilon, this epsilon sub I, we have the assumption that it is normal 0 sigma squared, right? So let me scroll down. So that's normal 0 sigma squared. So if I were to standardize it, divide it by its standard deviation, subtract the mean, right, which is just 0. So if I were to standardize that guy, I would get normal 0, 1, right? So theoretically, if you were to plot, right, these guys, a lot of times these guys are called just z, right? So if I were to plot z on my x-axis, and then epsilon divided by sigma, okay? And actually, let me go ahead and use instead of saying sub I, let me go ahead and say I'm going to order them, okay? So this is just like a subscript that just means I've ordered these values. Okay. So I order these z values and order those residual values, right? And if this is true, then where there's a particular z value, there should be exactly the same, right? Since they're both normal 0, 1, they should be exactly the same. Okay. So this is what a plot of these epsilon divided by sigma, what it would look like. It would be a straight line, right? Goes through the origin and it has a slope of 1. They're identical to each other, basically. Okay, and of course, these epsilons, right, so that's a very nice result, but epsilons are not observed, right? So we don't actually see the model error, but what do we see instead? We see the residuals. Okay, so I can order my residuals. Okay. Now, I do not know what sigma is. Remember, sigma is the model standard deviation, right? Sigma right here. But we have an estimate of sigma, and that estimate is s squared. So if I standardize, it's just divided by s. Sorry. So divided by s. So I'm replacing what I don't know. So I'm replacing epsilon with the residuals, and I'm replacing sigma with s. Right? And this guy is called the semi-studentized residual. Okay, so what's going on there? Why is it called that? So studentized means that you've replaced the population variance with an estimate of that. So we replaced the population variance sigma with s. So that's what studentized means. So why is it called a semi-studentized? Okay, in order to be truly studentized, then this s here should be the standard error of our residuals, right? Which are the observed values minus the predicted values. So you can figure out what the standard error, you can actually find a real studentized residual. You would need to figure out, well, what is the variance of yi minus yi hat, right? And it's just a little more complicated to, to estimate or to calculate. Okay, actually, it's easy to figure out what this equals, but then once you have the formula for it, it's a little more difficult to calculate. You can, of course, use the real residual, the real standard error, which is just going to be the square root of this guy. But it takes a lot more computation to do that. If you did do that, it would be called the studentized residual. Okay, but since we're not doing that, it's called the semi-studentized residual. Okay. So then what we do is we plot these semi-studentized residuals. So these residuals divided by s, right? Which is a reminder, what's s? S is the square root of the mean squared error, right? It's the square root of the sum of yi minus yi hat, right? Our residual squared divided by n minus 2. Okay? So remember, that's what s is. So this is very easy to calculate. Okay? And let's see, then we plot that against z, right? And so what we're hoping to see, so there's going to be some random variability. It's not going to be a very perfect straight line as it was if we had the actual model error terms, and if these actually followed a true normal distribution, you would see an exact line. But because, these are estimates, right? We're hoping to still see, going through the origin, a straight line, some random variability around that line, but we're hoping to still see a straight line. Okay? And that would be a pretty good indicator that this is coming from a normal distribution. Okay, that normal distribution assumption is reasonable. Okay? Now, so what happens when things go wrong? Right? So if you have normal error, so things going right, okay, first thing you would do is you'd see your histogram. You'd say, oh, wow, that looks great. That's a great histogram. Looks like a normal distribution. Okay? And then next thing you might do is you do this probability plot, and you'd see like a straight line. Okay? And you're pretty happy. All right? Things going wrong, you could have a skewed positive distribution. right? A skewed positive distribution would look something like this. When you do your histogram, you would have a bunch of observations that are just to the extreme to the right, right? Skewed positive is also right skewed. Right, and if you were in this situation, your normal probability plot, it would kind of look like that. Okay, so you'd have random dots, would not be going through a linear line, kind of be more curved. Okay, if you have a negative or a skewed negative, you would plot your histogram and you'd have a bunch of observations all the way to the left. So this is sometimes called a left skewed distribution. And your normal probability plot would look something like this. Okay. And then lastly, you can have heavy tails. Heavy tails is another very common one. All right. And so what this looks like on your histogram, it might be hard to tell that this is what's happening because you're seeing, oh, okay, it looks symmetric, it looks good, but you see how there's a large tail, right? Like a real normal distribution wouldn't have such a heavy tail. There's more observations in the tail than would be expected if you had a normal distribution, right? And by tail, I mean here and here. Okay? And so your normal probability plot, what it would look like is something like, it's like an S shape. Like a sideways S kind of. Okay? You see any of these, then you know you have a problem with your model assumptions. And if you have a problem with your model assumptions, then your confidence intervals, your test, your prediction intervals, all of those may be invalid. All right. So in the next video, I'm going to show an example where we actually, come up with this plot, the probability plot, and we're going to draw the histogram of our residuals.